The discovery of GN-z11, the most distant galaxy ever observed, is a groundbreaking achievement in astronomy, offering an extraordinary window into the early universe. Located over 13.4 billion light-years away, GN-z11 appears to us as it was when the universe was only about 400 million years old, a time when the first galaxies were just beginning to form. This galaxy's extreme distance is measured through its redshift value of 11.09, which indicates how much the light from the galaxy has been stretched as the universe expanded. This redshift is one of the highest ever recorded, placing GN-z11 at a critical period in cosmic history known as the Cosmic Dawn, when the first stars and galaxies started to illuminate the universe. What makes GN-z11 particularly fascinating is that it challenges previous notions about the timeline of galaxy formation. For a long time, scientists believed that galaxies took billions of years to form and evolve, but the existence of GN-z11 suggests that some galaxies were already well-formed and producing stars within the first few hundred million years after the Big Bang. This early formation hints that the processes leading to galaxy formation might have been more rapid and complex than previously understood. The discovery was made possible by the combined efforts of the Hubble Space Telescope and the more recently launched James Webb Space Telescope, JWST. These powerful instruments allow astronomers to peer back in time by capturing light that has traveled billions of years across the universe. For example, the Hubble Space Telescope, with its deep-field imaging capabilities, first identified GN-z11, and the JWST has further studied it, revealing even more details about its composition and structure. These observations not only push the boundaries of our understanding of the universe's early days, but also provide a benchmark for future discoveries of even more distant galaxies. Moreover, GN-z11's discovery has opened up new avenues of research, including the study of the first generation of stars known as population 3 stars, which are thought to have been massive, hot, and short-lived. Understanding these early stars and their role in galaxy formation can shed light on the conditions that prevailed in the young universe, including the reionization era, a pivotal phase when the universe transitioned from being opaque to transparent to light. GN-z11 stands as a testament to human curiosity and the relentless pursuit of knowledge, reminding us of how much more there is to learn about our vast and ancient universe. Imagine standing on the shore of an ocean watching ships sail away. As the ships get farther away, they appear smaller and fainter. Eventually, they disappear over the horizon, hidden from our view. The same principle applies to galaxies in the vast expanse of space. The farther away a galaxy is, the fainter its light appears to us on Earth. To detect these incredibly faint objects, astronomers rely on powerful telescopes, both on the ground and in space. These telescopes act as giant light buckets, collecting as many photons, tiny packets of light, as possible from these distant sources. But collecting enough light is only half the battle. The light from these distant galaxies has been traveling for billions of years, stretched and weakened by the expansion of the universe. To analyze this ancient light, astronomers use a technique called spectroscopy, which separates light into its component wavelengths, like a prism splitting sunlight into a rainbow. By analyzing the spectrum of a galaxy's light, astronomers can determine its composition, temperature, and most importantly, its redshift. You've probably experienced the Doppler effect with sound waves. As an ambulance with its siren blaring approaches you, the sound waves are compressed, making the siren sound higher-pitched. As the ambulance moves away, the sound waves stretch out, making the siren sound lower-pitched. Light waves behave similarly. When an object in space is moving away from us, its light waves are stretched, shifting towards the red end of the electromagnetic spectrum. This phenomenon is called redshift. The faster an object is moving away, the greater its redshift. By measuring the redshift of a galaxy's light, astronomers can determine its distance from Earth. The greater the redshift, the farther away the galaxy, and the earlier in the universe's history we are seeing it. This makes redshift an invaluable tool for studying the evolution of galaxies and the early universe. In 2016, astronomers using the Hubble Space Telescope announced the discovery of GN-z11, the most distant galaxy ever observed. With a staggering redshift of 11.1, GN-z11 is so far away that the light we see from it today began its journey towards Earth just 400 million years after the Big Bang. This means we are seeing this galaxy as it existed when the universe was only 3% of its current age. GN-z11 is a relatively small galaxy, only about 1% the size of our Milky Way. But it's forming stars at an astonishing rate, about 25 times faster than our galaxy today. This high rate of star formation is typical of galaxies in the early universe, which were smaller and more compact than their modern counterparts. The discovery of GN-z11 provided astronomers with an unprecedented glimpse into the universe's infancy, a time when the first stars and galaxies were just beginning to form. It offered valuable insights into the processes that shaped the early universe and the evolution of galaxies over cosmic time. Peering through the cosmic fog. Observing the early universe is like looking through a dense fog. The early universe was filled with a hot, dense soup of hydrogen gas that absorbed and scattered ultraviolet light. This cosmic fog makes it challenging to observe objects from the universe's first billion years, as their light is absorbed and scattered before it can reach our telescopes. To overcome this challenge, astronomers are constantly pushing the boundaries of telescope technology, developing new instruments and techniques to see farther and clearer into the early universe. One such advancement is the use of infrared telescopes like the James Webb Space Telescope. Infrared light has longer wavelengths than visible light and can penetrate the cosmic fog more easily. This allows astronomers to see objects that are too faint or too distant to be observed in visible light, providing a clearer view of the early universe. The significance of GN-z11. The discovery of GN-z11 sent ripples of excitement through the astronomical community. It pushed the boundaries of our observational capabilities, demonstrating that we can study galaxies that existed when the universe was just a fraction of its current age. But more importantly, it provided crucial insights into the early universe and the formation of the first stars and galaxies. GN-z11's high redshift and distance offered a glimpse into a critical period in the universe's history, known as the epoch of reionization. During this epoch, the first stars and galaxies formed, and their intense radiation ionized the surrounding hydrogen gas, making the universe transparent to light. By studying GN-z11 and other distant galaxies, astronomers can learn more about this crucial period of cosmic evolution and the processes that shaped the universe we see today. Hubble and Webb, our eyes on the distant universe. The discovery of GN-z11 wouldn't have been possible without the remarkable capabilities of the Hubble Space Telescope. Launched in 1990, Hubble has revolutionized our understanding of the universe, providing stunning images of distant galaxies and nebulae, and enabling groundbreaking discoveries like the accelerating expansion of the universe. However, Hubble has its limitations. Its observations are limited to visible and near-infrared light, which can be obscured by dust and gas in space. To peer even deeper into the early universe, astronomers needed a new, more powerful telescope. Enter the James Webb Space Telescope, Hubble's successor, launched in December 2021. Webb is designed to observe in infrared light, allowing it to see through the cosmic fog and observe the first stars and galaxies that formed after the Big Bang. With its advanced technology and larger mirror, Webb promises to revolutionize our understanding of the early universe and uncover even more distant and ancient objects than ever before. While we can observe the effects of gravity on galaxies and their movements, there's a significant portion of the universe's mass and energy that we can't see directly. This mysterious component is known as dark matter and dark energy. Dark matter doesn't emit, absorb, or reflect light, making it invisible to our telescopes. However, its gravitational influence can be observed on the motion of stars and galaxies, suggesting that it makes up a significant portion of the universe's mass. Dark energy, on the other hand, is a hypothetical form of energy that permeates all of space and is thought to be responsible for the accelerating expansion of the universe. The study of distant galaxies like GN-z11 provides valuable clues about the nature of dark matter and dark energy. By studying the distribution and movements of galaxies in the early universe, astronomers can refine their models of dark matter and dark energy, gaining a deeper understanding of these elusive components of the cosmos. Distant galaxies are not all alike. They come in a wide variety of shapes, sizes, and star formation rates, reflecting the diverse conditions present in the early universe. Some are small and compact, like GN-z11, while others are larger and more extended, suggesting that galaxies have evolved significantly over cosmic time. By studying the properties of distant galaxies at different redshifts, astronomers can trace the evolution of galaxies over billions of years, from their formation in the early universe to their present-day forms. This allows us to understand how galaxies assembled, how their star formation rates changed over time, and the role of galaxy mergers and interactions in shaping their evolution. While the discovery of GN-z11 and other distant galaxies has significantly advanced our understanding of the universe, it has also raised new and profound questions. How did the first stars and galaxies form so quickly after the Big Bang? What is the nature of dark matter and dark energy? Are there even more distant galaxies waiting to be discovered? These questions continue to drive astronomers to explore the cosmos, pushing the limits of technology and our understanding of the universe. The search for the most distant galaxies is not just about breaking records. It's about unraveling the mysteries of our cosmic origins and our place in the grand tapestry of the universe.